guys. Good morning. Time is almost 10:30. So I see some of you. Maybe like for 2-3 more minutes. We'll start. So maybe by that time we will see what all we saw last class. Right? Okay. So I think we started with what are colligative properties. Right? So can someone tell me what are colligative properties? How do you define them?
It's independent on the nature of the substance, but it's depending on the amount.
1 second. There is 1 second, guys. Yeah, can someone now speak?
So can you hear me?
Yeah, please. Yes, sir.
So colligative properties are properties which are independent on the nature of the substance, but dependent on the amount of substance we use.
Absolutely. Right. So I don't care what is there, right? But all I care is how much is there. Right. So based on that, the properties will change, the values will change, and those properties or values are what are called as colligative properties. Okay. So what is the main application of using colligative properties? Why do we use colligative properties? To do what? Yeah, for what? For what we use colligative properties? I mentioned this, isn't it? Anybody? You can even put in the chat box if you're not able to unmute and speak. What do we use colligative properties for? It can be a guess from what you have learned. Maybe just open your mouth and say something.
The property is independent of the substance nature, but they're dependent on the quantity of the substance present.
Understood. That is colligative properties. That is the definition of colligative properties. What do we use colligative properties for?
Relative lowering vapor.
Elevation of boiling point.
Yeah, that is two of the colligative properties. Okay. So with those things, what are we going to do? What are we trying to do? I mentioned this, isn't it?
Substance present.
Find out the number of substance present.
Find out the number of substance present. Okay, you're coming closer, but not exactly.
Identity, sir. That is to find the solute.
To find the solute, see, the entire essence of colligative properties then goes. If with colligative properties you are able to find what is there, that means you're telling what is the solute. Are we not, say, going wrong by the definition? Because definition says I don't care what is there, but I just care how much is there, right? So from the definition itself, I think you should be able to guess. And little thinking from previous class, what I told you, you should be able to answer this question. I don't care what is there, but I just care how much is there, and then think, what are we going to use it for?
The concentration.
A little correct. Okay. Little more. Can you dig in?
The amount of substance.
Thank you. So you're going to find, okay, it's actually not correct, right? Okay, little more closer. Again, come on, build upon this. Someone said amount, someone said concentration.
The molar mass.
Yes, that's exact. Molar mass of what?
The substance.
What substance? Tell me the exact thing. Molar mass of what? There are only two substances, right, in a solution?
Sir.
In a solution, there are only two substances.
Sir.
Sorry?
Molar mass of solute.
That's what we are going to find, right? So I give you an unknown solution. Say you know what is the solvent. Say water. You don't know what you added in that, the solute, right? So even though you don't know what you added, right? But with the help of colligative properties, I will be able to find the molecular mass of this unknown solute. That is the application. Please remember this. Okay. So what are we going to do with colligative properties? We are going to find the unknown molecular mass of an unknown solute. We don't even know. We don't even have to know what is there, right? An unknown solute X. We could have even solved problems. You can just check the previous classes, right? We would have solved two problems. One with for relative lowering of vapor pressure. I think the other one I think is for relative. Elevation and boiling point. I think we should have solved 2-3 problems. Did we solve problems on elevation and boiling point? Did we? I think one problem.
One question.
Okay, one question. So I think in both the questions, right, you would have seen what you are trying to find out there. If you see the questions, you will say the question was find the molecular mass of unknown solute. That's what they would have asked you, right? And that's exactly what we're trying to do, right? So with the help of all the other measurable properties, I'll be able to measure with an instrument. Say for example, I take relative lowering of vapor pressure. Right. So can someone tell me the equation for relative lowering of vapor pressure? What is the formula? Relative lowering of vapor pressure. Can
P
someone
by
tell me?
PA naught is equal to XP.
Right. So del P divided by PA naught. If you put A here, you have to put XB here. So it's the mole fraction of the other one. Right. So you can understand this can be measured. Obviously, this can be measured with the help of some instruments. Barometers are there. Diaphragms are there. You'll be able to measure pressure. That is not a big deal. Vapor pressure only. Right. Again, mole fraction, if you check, mole fraction, I know XP will be equal to number of moles of B plus number of moles of B plus number of moles of A. Say B, assume that B is a solute, right? So please understand, again, in this, number of moles of A, number of moles of B, how do you write? Given mass of B divided by the molecular mass of B, same way for this. And in this case, it would be given mass of A divided by the molecular mass of A. Say, assume that A is the solvent, B is the solute. Okay, now I told you this quantity can be measured, right? And you know what you're adding, right? You know how much grams of that particular solute you're adding. Even though you don't know the molecular mass, you are measuring it, isn't it? You are measuring it, how much you're adding, and then you are adding it to the solution for the solvent, right? So this value is also known, given mass of the solute. Obviously, you know the given mass of solvent because you are only taken it. You pick, if you know what is the solvent, obviously you know what is the molecular mass of solvent. Say water means 80. Right. So what do you see? The only thing which you cannot find or which you cannot measure and you have to find through calculation is this. That is the molecular mass solute. Okay, right? So that is the whole point of colligative properties. Right? Okay. So we went on to see what is this relative lowering of vapor pressure, and I mentioned that if you find it difficult to do problems with this, you can do the same exact problem with the help of Raoult's law also. I think we took a problem and then we solved it in both the ways using this as well as Raoult's law, and you will get the same answer. Okay, fine. So then we went on to see how does that elevation and boiling point. That is the second colligative property, right? So can someone tell me a defined boiling point in terms of vapor pressure?
Point
yeah.
will be like the atmospheric pressure. The point.
Okay. Yeah. Okay.
Temperature, it is vapor pressure is equal to the atmosphere.
Okay. Right. So correct. All 98% of whatever you told is correct. There's something missing.
Temperature at which boiling.
Yeah. That you told. So yes, the exact definition is
temperature at which the vapor pressure of the liquid phase is equal.
That's the point. Vapor pressure of the liquid phase. Yes. Right. So you have to tell that it is the temperature at which the vapor pressure of the liquid phase, right, becomes equal to that of the atmospheric pressure. Right. Okay. Fine. Now we have to understand why is there elevation and boiling point. So if at all I had 100 degrees Celsius for pure solvent water, right? Now if you add a salt, say NaCl for that matter, right, you will see that the boiling point has increased to say 101 or 102, right? And we even saw why is this happening, because as far as we understand, when I have the pure solvent, I will have some vapor pressure. Right now, if I add the solute to it, we already saw it is going to block some of the surfaces and stuff. So the amount of liquid going to the vapor phase is decreasing. Right. So obviously, if the amount of vapor itself is decreasing, obviously the vapor pressure is decreasing, right? So for now, for me to make that decreased vapor pressure to be equal to the atmospheric pressure, obviously I have to supply more temperature. It's as simple as that, right? Okay, so that is why we see there is an elevation in boiling point. Okay, now there was an equation, right? Now, can you tell me what was the equation for elevation in boiling point?
So delta T is equal to
Hmm.
KB into M.
KB into M. Okay, so delta TB is equal to KB and
Monal,
M, right? Right. So this M is what?
molality.
Molality.
Molality. Right? And this delta TB is the change in temperature. Say if it's 101 and 100, the difference would be 1, something like that. Right? And this KB, there are some names to this. What is this called as? KB?
Molar elevation constant.
Okay, one of the name is molar elevation constant. What is the other one?
Ebuloscopic.
Ebullioscopic constant. Okay, fine. So this is all what we saw last class, right? And even did a problem on this. Very simple. Okay, fine. So next we'll move on. We have two more colligative properties. Okay, we'll see what are we going to do with them. I think I already introduced you to the other one. The other one is depression and freezing point. Okay, we'll see that. Any questions till now, people?
So I have a doubt. Does
Yeah.
KB have a value?
Yes, it has a value. It depends on the solvent. For benzene,
It
it will have a
varies
value.
from different
Yes,
compounds.
it varies from solvent to solvent. Water will have one value, benzene will have some other value, ethanol will have some other value. It depends on what solvent you use. And that value will be given in the question. Don't worry about it.
Okay, sir.
Okay, right. Fine. So yeah, we'll move on. We'll move on to the next colligative property. The third one is depression in freezing point. Okay, just now how we saw there is going to be increase in the boiling point. Now when I'm going to add the solute to that particular liquid, to that particular solvent, all I'm going to see is that the liquid's freezing point is decreasing. Okay, fine. So first what we do is, first we'll take the definition of freezing point with respect to the vapor pressure, and then we'll try to understand this. Why is there a depression? Take down the definition first. And guys, one more thing. I don't know how many of you are sitting along with your textbooks. Sorry. How many of you are sitting along with your notebook and a pen, right? It is mandatory, or I would say it is really advisable for you to take notes. I think people who have already been in my 11th class, I have been telling this for a long time, right? So whatever comes out of my mouth is very important. Okay, whatever comes out of my mouth. So if you can quickly note it down somewhere, like write a running notes, you see the very beautiful thing about notes is the same chapter which is given in your book is around 10 to 15 pages, right? But if you're going to write down notes, right, maybe you will be get around 10 pages, right? But that will be very short notes, because look at the size of your book and look at the size of your notebook. There 10 pages and your notebook 10 pages is really not the same, right? So if at all you're going to study through a chapters in your NCERT textbook, say it will take another 2 hours, 3 hours. The same thing, if you're going to go through the notes, it will take half an hour for you to complete a chapter. Trust me on this. Notes are essential, mandatory, right? So if anybody is not sitting along with your notes, please take down your notes and start writing and record whatever comes out of mouth. Whether I write here or whether I ask you to take down, irrespective of whatever it is, if you are able to grab whatever I'm able to say and note it down, it is going to be really helpful for you. Maybe not now, but when you're going to revise your stuff, when you have to quickly revise for your exams, definitely notes are going to be very, 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 very helpful. Trust me on this. Okay, and so many of you, I felt in 11th class, felt problems, right? You faced some problems because you were just listening to the class. See, the information we have is huge, right? So even though you are a Newton or an Einstein, right, you cannot remember everything. Even me, including me, whomever it is, even you are a brilliant genius, right? Remember this, you will not be able to remember everything. See, we are going to have almost like I don't know, 50 classes, right? All 50 classes you'll remember. You are that confident? If you are confident, please come down. I'm telling you, you cannot do it. Okay, so the easiest way is when you listen to the class, take a notebook and start writing. Okay, so if at all you are not doing it till now, please start. Right, and till now, whatever you have seen, if you're not taken down anything, ask your friends if they've taken down notes and get it from them. Right, people who are coming for offline classes, I saw them take notes, well and good, but I don't know really what is happening in online. If you are not, please take down. I understand that someone will be using phone to listen to the classes and stuff. Like sit in a chair, keep the phone near the wall or something, and then you start writing. Okay, I know it's difficult, but again, it's only for this 1.5 hours or 1 hour of class. After that, again, you're not doing. After that, it's going to be very easy. Okay, fine, cool. So we will take the definition for freezing point with respect to vapor pressure. We already know what is the freezing point, isn't it? Freezing point is temperature at which liquid gets converted to solid. That we know already, right? Now, but with respect to vapor pressure, we'll see how it goes. Please take down. It is the temperature at which the vapor pressure of the liquid phase, becomes equal to that of, or becomes equal to the vapor pressure of the liquid phase becomes equal to that of the solid phase. Becomes equal to that of solid phase. Okay, right? So from the definition, I think if I have to repeat it, right? So it is the temperature at which the vapor pressure of the liquid phase becomes equal to the vapor pressure of the solid phase. That's what is given in the definition, right? Okay. So obviously we can understand solids also will have some vapor pressure, because say if you have solids like naphthalene, right? You know what is naphthalene? We use in your bureaus for making sure that no insects comes, making sure it has a good smell and stuff, right? So these naphthalenes are solids, but they can eventually sublime. You know what is sublimation? Sublimation is conversion of solid to gas directly, right? So obviously certain solids are capable of having these vapors around them. Again, same phenomena. The vapors will exert some pressure on the surface of the solid. That again is the vapor pressure, right? So what here tell is that the vapor pressure of the liquid phase, what is the temperature at which the vapor pressure of the liquid phase becomes equal to the solid phase? What is the temperature? That temperature is what is called as your freezing point. Okay, right, fine. I think from this definition, right, please understand people. Now, if I'm going to decrease the temperature, right, if I'm going to, I have a liquid, it has some vapor pressure. If I'm going to decrease the temperature, what do you think will happen to the vapor pressure? Again, I repeat the question. I have a liquid, which is pure liquid. I have some vapor pressure. Okay, right. Now, when I decrease the temperature, what will happen to the vapor pressure? Decrease or increase? Decrease. Obviously, right? Because obviously, you know, it's the ulta of whatever we saw. If I'm going to increase the temperature, what is going to happen? The number of liquid molecules going to the gaseous phase is increasing, and obviously the vapor pressure also will increase. This is exactly ulta. When I'm going to decrease the temperature, the capacity of the liquid molecules to go to the vapor phase is decreasing. Obviously, the number of gaseous molecule is less, and obviously the vapor pressure is also less. Okay, right? So when temperature decreases, vapor pressure also decreases, right? So you will decrease, right? So there'll be a now say the vapor pressure of, say this is okay. Assume that this is the okay. Say T1, vapor pressure of 1. This is the liquid. Okay, so you go on decreasing the temperature. Say you reach the freezing point. Okay, so in this only I have the vapor pressure of the solid. Okay, right. So now this vapor pressure of liquid at last will become equal to the vapor pressure of the solid phase, and that temperature is what is called as your what to say, freezing point. Okay, so this is where the solid lies, and it has some vapor pressure. So initially you will have some vapor pressure in the liquid. So if you keep on decreasing the temperature, vapor pressure also decreases, and eventually the vapor pressure of the liquid phase becomes equal to that of the solid phase. Right, now when I'm going to add a solute to this, I have, this is a pure liquid. What the liquid I mentioned is a pure liquid, only solvent. Right, now if I'm going to add, right, if I'm going to add some solute to this, right, is it not, you already understand that this vapor pressure will decrease? We already saw this, right? Once you add a solute, the vapor pressure itself will decrease, and obviously the entire thing reduces, right? Eventually everything reduces, and you see there is going to be a depression in freezing point, that is decrease the freezing point. Okay, right, fine. So this we understood. What is the freezing point? Why is there a depression in freezing point? Yes, after adding the solute, obviously. Right. Okay. So now we'll try to understand it quantitatively, mathematically, what is going to happen. Right. Okay. Now it is going to be very, 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 very similar to the elevation boiling point, except that here we're going to talk about the freezing point. Right. So directly I'm going to give you the equation. The equation goes like this: delta TF, depression in freezing point. Right. This term, delta TF, change in freezing point. Right. So now delta TF will be equal to kV. It is going to be kF into m. Again, m is the molality, right? And delta TF is the depression in freezing point, right? And this kF again is a constant. It's called molal depression constant. Just like you have how you have molal elevation constant, we are going to have molal depression constant, or it is also called as cryoscopic constant. It's also called as cryoscopic constant. Okay, right, fine. So again, a very, very simple equation. Delta TB is equal to KB into M. Same way, delta TF is equal to KF into M. Right, fine. I think we should solve some problems here, right? And then we'll go on to the last colligative problem. Okay, right. Any questions till now, people? I hope everything is clear. If you have anything, please ask. Fine. Let me take a question. Oh, 1 second, guys. I was looking for a good question. Just wait. Okay, so I think this is a direct question we can take. Right. Okay, fine. Please take note, guys. 15 grams, 15 grams, 15 grams of an unknown solute, 15 grams of an unknown solute is dissolved in 450 grams of water, right? 15 grams of an unknown solute is dissolved in 450 grams of water, right? The solution freezes. The solution freezes at 0.34, okay, minus 0.34 degrees Celsius, right? The solution freezes at minus 0.34 degrees Celsius. Okay, now they're asking what is the molar mass of the solute? Okay, what is the molar mass of the solute? Okay, and they have given Kf for water to be how much? 1.86 Kelvin kg per mole, right? So the Kf for water is 1.86 Kelvin kg per mole. I'll repeat the question. 15 grams of an unknown solute is dissolved into 450 grams of water. The solution freezes at minus 0.34 degrees Celsius. What is the molar mass of the solute? Given that the Kf is the such. Okay, go for it. It is exactly similar to the problem we solved for elevation boiling point, except that here we have freezing point. Try to get the answer. Go for it.
Sir,
Yeah.
convert the temperature to take
Sorry.
sir.
Okay. So you look at here. He's asking whether I have to convert the temperature in terms of Kelvin. Not required, right? Why is it not required? Is because say I have 273 Kelvin. Okay, maybe I'll drop this part. 1 second. Right. Say I have 0 degrees Celsius and 273 Kelvin, and say I have some 100 degrees Celsius and 373 Kelvin. Okay. Now you take the difference in both of them. What will be the difference in both of them? 100, right? So as long as you are not going to use the temperature in any other case, say multiplying with something or adding with something, right? You don't have to convert it.
Sir, okay. But the constant's value is given 1.86.
Absolutely. But the thing is, that's what. Say, if whatever the temperature is given, you convert that to Kelvin and take the delta TF. That delta TF will be same, that magnitude I'm telling, right? The number will be same as that you take in the degree Celsius. So if you want to convert and use it. Not a big deal. But you're going to get the same answer. Okay? Right. Fine. Okay, so they have given the solution to freezing point, but don't you want to have two freezing points? One
Yes.
is for the solution, the other one is for the solvent. What is solvent here?
Water.
Okay, so what is the value of freezing point you'll take?
0 degrees Celsius.
Absolutely, right? So like this in questions, they will not give you, if at all other than water, if they give you anything else, just like last question we solved for elevation and boiling point, they have given you the boiling point of benzene, because generally we don't know what is the boiling point of benzene. But water, we should know what is the boiling point, we should know what is the freezing point. Directly, they will not give it in the question. Please remember this. Okay, right? So in this case, you have to take the freezing point of water, and that is 0 degrees Celsius. Okay, right? So it will be what? Delta TF, if you have to calculate, it will be 0 degrees Celsius minus 0.34 degrees Celsius. So it will be 0.34. That will be the delta TF. You know how to calculate molality. Kf is directly given.
how to calculate the moles for an unknown solute, sir?
Yeah, that's what. From the number of moles formula, what you have? Given mass by molecular mass.
Molecular mass, sir. So we don't know the
Molecular mass is what is the question they're asking? You have to find the molecular mass, right? Okay, so it's 0.34 as we calculated. That is delta TF. KF is 1.86. That is given in the question. And molality, we know number of moles of solute divided by mass of solvent into 1000. Obviously, because we are using grams, right? So number of moles of solute, I don't know. So let me keep it as number of moles of X. I don't know, right? Okay, divided by what is the mass of solvent? What is given in the question?
450 gram.
250 or 450?
450, sir.
450, right? 450 into 1000, right? Again, let me substitute for the number of moles also for the solute, because given mass is known, only the molecular mass is not known. So 0.34 is equal to 1.86 into number of moles is, I think, 15 grams of the solute divided by, I don't know what is the molecular mass, into how much? 450 into 1000. So at least if you have got this much expression, you're on track.
Sir, is the answer 183.5, sir?
I am not sure, Kanna. Let me check. What question is this? Where did I take the question from? What? Okay, I don't have the answer with me, guys, because I don't know which question I took. But you can solve, not a big deal, right? If you have gotten this much correct, then all you have to do is calculations. That's it. You just have to find what is the molecular mass of this. That's it. Okay, simple formula substitution. Okay, fine. We'll go to the next question. I hope everybody understood. Is there anyone who didn't understand? Simple formula substitution. We didn't do anything here, right? Okay, fine. If you have still little doubts, you can please ask me. Right? Okay, go to the next question. Okay, take this question. So this question was asked in All India 2010. So let me see if you can solve it. Okay. What mass of ethylene glycol what mass of ethylene glycol, they have given the molecular mass of this to be 62. Okay. Do you know what is ethylene glycol? Anybody knows what is ethylene glycol? Yeah. What are generally glycols? Okay, I don't. Obviously, you wouldn't have studied alcohols after. Yes, but basically, glycols are in an organic compound. If we have two carbon atoms having adjacent OH, that is what is called as glycol. So if it is ethylene glycol, it's very simple. CH2OH, CH2OH. That is what is the formula. Okay. So anyways, now you don't have to know all this because they're directly given to the molecular mass. Okay, fine. So what was I? Yeah. So what mass of ethylene glycol must be added? What mass of ethylene glycol must be added to 5.5 kg of water? 5.5 kg of water to lower its freezing point. To lower its freezing point to minus 10 degrees Celsius, right? To lower its freezing point to minus 10 degree Celsius. Okay, and obviously KF for water is same thing as we used last time, 1.86. Okay, KF for water is 1.86 Kelvin kg per mole. Okay, I'll repeat the question. Right, what mass of ethylene glycol of molecular mass 62 must be added to 5.5 kg of water to lower its freezing point to minus 10 degrees Celsius? And KF for water is again 1.86 Kelvin kg per mole. Go for it. Right. So this time you know what is the solute, ethylene glycol. You know what is the molecular mass, but they're asking you how much of this ethylene glycol I should add so that the freezing point changes from 0 to minus 10. Right. Again, it's all in the formula. Only formula if you substitute, you are going to get the answer.
Sir,
Yeah.
is the answer 1.833 kilograms?
1.833 kilograms. Let me check. Now I'm having the question properly. Okay. So it is. Yeah. What did you say? 183.333?
So 1.833 kilograms.
Yeah, correct.
Okay.
Answer is right. Yeah. Right, same formula. Right, I think just again formula substitution. The last time they were asking you molecular mass. In this case, they're asking given mass. That's it. Right, that's the only difference. Okay, so delta TF is equal. Delta TF is equal to KF into M. So delta TF, I understand it's 10. 0 minus of minus 10. Right? Initially it was 0. Now it is minus 10. So minus of minus 10 will become plus 10. So KF is 1.86. Molality would be number of moles of ethylene glycol. Okay, CH2OH, CH2OH divided by mass of water, mass of solvent. Mass of solvent is 5.5 kg. So you don't have to put 1000 here. Please understand, right? This 5.5 is in kgs. So that's why I'm not putting any 1000 here. If you want to convert it into grams, then you have to put 1000. Okay, fine. So this will be 10 is equal to 1.86. Number of moles of ethylene glycol will be given mass of ethylene glycol. I'll write this Eg, right? Given mass of ethylene glycol divided by the molecular mass of ethylene glycol, which is given in the question to be 62. Right? So that's it. This is the number of moles, and other thing stays into 5.5. Right? This is what you have to find. That's it. And the answer would be, as she said, it will be 1.833 kgs. Or you can write it as 1,833.3333 grams. Anyway, you'll get the same answer. I mean, you'll get the marks. Okay, so you understand that maybe we are solving more problems for depression and freezing point, lesser problems for elevation and boiling point, but the problems will be exactly similar. No change, except that there it is freezing point, here it is boiling point. That's it, right? So either of the case, either you're gonna get question from elevation boiling point or from depression and freezing point. The methodology is exactly same, no difference, right? Okay, so I think maybe we will solve a little more tougher question, and then we'll go on to the next colligative property. And one more thing, people, right? So this mistake we commonly do. So we take 0 degrees Celsius as 273 Kelvin, isn't it? Right? But for your calculation purposes, especially for board exams, you should not use it as 273. You should use it as 273.15 Kelvin. Okay, please make a note of it. Okay, right? So for generally we take 0 degrees Celsius 270 approximately, and we do the calculations, right? But in your board exams or whenever the test comes in your school or whatever it is, you must use 0 degrees Celsius as 273.15 Kelvin, not 273. Because of this 1 5 and calculation mistakes will come, you lose marks. Okay, make sure you remember this, right? Okay, fine. I'll take down the question. Please take down. A 0.1539 m, small m, 0.1539 small m. What do you mean by small m? Small m is molality, right? Okay, so 0.1539 m, small m, solution of cane sugar, right? 0.1539 m, solution of cane sugar. What is cane sugar? What is cane sugar? Let me see if anybody can answer this. What is cane sugar?
Sir.
Nobody knows.
Sugar cane. Sugar.
Ah, okay, fine. So sugar cane is a sugar. So what is that?
Organic sugar.
Sugar cane is a sugar. What sugar is there?
Sucrose.
What is the name of the sugar?
It's sucrose, sir.
Ah, that's what I want. It's sucrose, right? So like this, lot of questions you'll see in your board exams also, or in your school exam called solution of cane sugar. Cane sugar is nothing but sucrose, the sugar we use in our houses. Okay, it is sucrose. Oh, formula for sucrose?
C11.
C11?
H6.
No. See, it is. See, the thing is, I will maybe if you go to the chapter called biomolecules, which is a chapter organic, Maybe you will be able to remember this a little more better, but still, let me tell you how you remember this. Okay, what is the formula for glucose?
C6H12O6.
Okay, that we know, right? So C6H12O6 is what is the formula for glucose. Now, what you do for sucrose is you multiply this by 2. Okay, so what will you get? You will get C12H24 O12. This is what you'll get. Okay, now what you do is once you multiply this, it's not exactly double of that. From this, you remove a H2. That means 2 hydrogens and 1 oxygen you remove. Right? So what will be there? C12, H22, O11. This is what is. Okay, right? So you take the glucose's formula, multiply it by 2, remove a water molecule. You'll end up with
C11 should come, right?
Sorry. Why C11? C12 only. Okay, I'm sorry. When you said C11, I said correct. No, it's not C11, it's C12. Okay, so it's C12, H22, O11 is the formula, right? And for this big formula, you'll find the structures. Like what is the formula? What is the structural formula? You'll see when you go to biomolecules chapter. Even for this, you'll see. Okay, for now, we'll concentrate on the question we have in our hands. Okay, so 0.1539 small m solution of cane sugar, molecular mass 342. Cane sugar's molecular mass is 342. Has a freezing point of 271 Kelvin. 271 Kelvin. Right. Okay. Now they're asking, what will be the freezing point? What will be the freezing point of an aqueous solution of glucose or aqueous solution? Wait. Once again. So what will be the freezing point of an aqueous solution? What will be the freezing point of an aqueous solution containing 5 grams of glucose, 5 grams per glucose, 5 grams of glucose per 100 grams of the solution. 5 grams of glucose per 100 grams of the solution. Okay, I'll repeat the question, people. Right. A 0.1539 small m solution of cane sugar has a freezing point of 271 Kelvin. Right. Okay, they're asking, what will be the freezing point of an aqueous solution containing 5 grams of glucose per 100 grams of solution? Right. It's not just 5 grams, it's 5 grams per 100 grams of solution. Okay, go for it. Think about it. How do you solve this? Anyways, I'm going to help you. Right. Try to get the sketch of how do you do the problem.
So I have a doubt. Here del TF get calculated by subtraction, right?
Yes. So they have given you the freezing point of the solution. So obviously what you have to take is the difference in freezing point between the pure solvent and the solution.
Okay.
Yeah.
So
And
what
in
is the KFB?
KFKB, go for it. It's not given in the question, that means you have to do something about it. Right. And that is not useful actually in this question. KF is not useful. So think of a smart way.
Sir, is the answer 263.38 Kelvin, sir?
263 point some Kelvin. Okay, I'll check. So this is short answer. 260. Yes. What did he say? What is the answer?
Sir, I got 263.38 Kelvin, sir.
263.38. No. But yeah, it is in 260s. So your answer is like say a little far away from the answer, but yeah, but not correct. So this is just given to this kind of problems are just to confuse you, right? But there's nothing
Is it
taking this from.
268, sir?
Yeah, it's 269 actually to be exactly correct. Okay, the answer is 269. Yeah, so I think it's pretty easy, right? They just have to use the formula 2 times. Delta TF is equal to KF into M, right? So they have given it given the solutions freezing point to be 271, right? So we have to supply, we have to minus 273.15. If you have forgotten this, the answer will come out wrong, right? The freezing point of water is 273.15. That's why I mentioned it last time before we even start the question. Okay, minus 271 is equal to KF, which we don't know, which is not given in the question. Molality we can find. Molality is directly given 0.1539. No issues. Okay, so can I say this value would be 2.15? Okay, so 2.15 is equal to KF into 0.1539. That this is for I'm doing this for the sucrose solution or the cane sugar solution. All this is given in the question. Okay, fine. Now when I go for say let me call it as delta TF1, right, for sucrose, and let me call it as delta TF2 for glucose. Okay, so now for glucose solution, right, delta TF2 is equal to KF, same KF only, because both are aqueous solutions. In both cases, the water is the solvent. I told you KF depends on the solvent, right? So in the first case also it's water, second case also it's water. So KF value is not going to change. KF is KF. Okay, fine. Now into, now I have to calculate the molarity. Molality. Okay, so molality, look at this. They have given 5 grams of glucose per 100 grams of solution. Right? Okay. Now, what do you mean by this? That means if I have 100 grams of the solution, in that 5 grams is glucose. Is that what I understand? Isn't it? Now, for molality, you require number of moles of glucose. Yes, that we'll be able to find. And also, I require what is the mass of the solvent. Right, but what they're giving you a solution. Okay, let me clarify this. Okay, so if I say that there is 5 grams of glucose in 100 grams of solution, can I say 5 grams of glucose is dissolved in 95 grams of water? Can I say this? Yes or no?
Yes, sir.
Right, totally 100 grams. In that 5 grams is glucose. What is the rest amount? Rest amount is solvent. And what is rest amount? Rest amount is 95 grams. Isn't it? Right? Okay, fine. So now what I need is, I need basically, you go for the definition. What is the definition for molarity? Sorry, molality, the number of moles of solute present in 1000 grams of water. Sorry, 1000 grams of solvent. Isn't it? So now you have what is the amount of solute present in 95 grams of the solvent. So what I do, I have to calculate it for 1000 grams. So I hope you know the crisscross method. If you have 3 values and 1 value, you have to find. This is how you do. Say X grams of glucose. Say it is going to be in 1000 grams of water. Okay. Now, if at all, you can do one more thing. You can directly calculate the number of moles, right? So if I like, don't get confused. Do not worry. It's very simple, right? So instead of writing it like this, I can write 5 divided by 180 moles of glucose. Can I write? Is it not? 5 is the given mass. Molecular mass of glucose is 180. So 5 divided by 180 moles of glucose is present in 95 grams of water. Now what I need is the number of moles present in 1000 grams of water. So directly I can easily find that X moles of glucose is present in 100 grams of water. And this X you find is the molality. That's what is going by the definition. Please don't get confused, guys. Right? Or if you're finding it very difficult, you chuck all this. Okay. One thing you understood is 5 grams of glucose in 95 grams of water. Done? Okay. So that is what is there in your hand. Okay. So molality, how do you find? Number of moles of glucose first, right? Number of moles of glucose will be given mass divided by the molecular mass of glucose 180, right? Divided by the mass of solvent. What is the mass of solvent? Mass of solvent now just now we found out to be 95 grams. Don't put 100 here. 100 is the total solution. In that 5 grams is glucose, 95 grams is water. And that's it. Now you have to multiply this by the numerator. Now you have to multiply this by 1000. Okay, right, fine. Now, one way of doing this problem is you know this value, calculate Kf and substitute that Kf, and you will be able to find the delta Tf. Again, I repeat. This value for sucrose. You can calculate Kf and substitute the Kf value here, and this value is known. You can find what is delta Tf. But if at all you don't want to double calculation, right? So let me take this equation as 1 and this equation as 2. What you do is you do 1 divided by 2, right? So if you do 1 divided by 2, what will you get? Kf will get cancelled. So you don't even have to calculate Kf. Okay, so or the other method will be finding Kf and substituting here. Or you can divide these two equations so that Kf gets cancelled. Right? So you'll have 2.15 divided by delta Tf2, which is here, right, is equal to Kf gets cancelled, and this value divided by this value. Whatever the value. And with all the values are known, you will be able to find what is the depression in freezing point. Right? They're not asking you a depression freezing point. They're asking you what is the freezing point of the solution. Right? So once you find the depression freezing point, say I write it here, if delta Tf2 is found out, that is equal to 273.15 minus the Tf of the glucose solution. And this is what you have to find. Okay? Once you find the delta Tf from all these calculations, right? They're not asking you depression and freezing point. They're asking you what is the freezing point, right? So that you have to find. So delta Tf2, whatever you calculate here, will be equal to the freezing point of water, that is 273.15 minus the freezing point of the solution, and that is what you have to find. Okay. Any questions? Everybody understood? Please give me a yes if you understood. Everybody, at least in chat box or
Yes, sir.
Okay, 1,
Yes, sir.
2,
Yes, sir.
3,
Understood, sir.
4,
Yes, sir.
5,
Yes, sir.
6,
Yes, sir.
7. That's it. There are so many. Okay, there is one in the chat. Okay, 8. Okay, guys, I hope you all understand. If you do not understand, please let me know. Right? So it's very simple. 2 times I'm just using the formula. Right? The only confusion, the only difference is this one, the 5 divided by 180 by 90, how it came. Right? They have given 5 grams per 100 grams of solution. 5 grams of glucose per 100 grams of solution. So what I can understand from that, 5 grams of glucose is present in, okay, 100 grams, in 100 grams, 5 grams is glucose. Obviously, rest 95 grams will be water. And that's exactly what I used. 5 divided by 180 is the number of moles of glucose divided by mass of solvent, that is 95 into 1000. This alone you understand. Rest all are mathematics. That's it. Okay,
So what was the answer for this?
269 Kelvin. TF, that value is 269.
Sir,
Yeah.
I got the same answer, sir, but instead of 95, I did it as 100, sir. The mass
Ah.
of solvent. I still got the answer.
Strange. Maybe check it one more time. Maybe using calculators.
Okay, sir. I'll
Or
just.
maybe the answer given in this also they have done the same blunder. One second, let me check. 16 question, not answer. No, they have given 95 only. Right? They have used 95 only. Please check a calculation.
Okay, sir.
Right. Fine. Okay. Right. So that's it. That's about depression freezing point. That's about elevation boiling point. And guys, don't worry about why we didn't do so much problems in elevation boiling point. It is similar. Exact problem I can ask even in elevation boiling point. Okay. Right. Fine. So we'll move on to the last colligative property. And then we just have two more topics left. One is the last colligative property, and the other one we'll see later. Okay. What is the time? Okay, we have half an hour. Okay, cool. So the last the last colligative property, fourth one is osmotic pressure. Okay, right? The most important of them all. We have seen this is the fourth one. This is the most important colligative property among all the four. Okay, fine. So we'll start from the basics, right? First, we'll try to understand what is osmosis. We already know this, isn't it? Right? Can someone tell me what is osmosis?
Loss of water.
Loss of water. Is that how you define osmosis? Any biology students or anybody who's interested in biology? By the way, any biology students are here? Anybody? Yeah, you can give me a yes.
It's a movement of the solvent.
Okay, movement of the solvent.
Solvent movement related.
Okay, I understood only movement of solvent. After that, yes. Yes, Karna, please tell me. Movement of solvent. You're correct.
So something movement in liquids, sir.
So it's 9th standard definition, fine, sir.
Yeah, any definition.
It's the movement of water from a concentrated body to a less concentrated body.
Okay, fine, right. Almost correct. This is exactly what we are going to see also here. Now, please understand, people. Right, there is one thing called osmosis. There is another thing called diffusion. Right. Now, both the things have almost similar definitions.
So water moves from high pressure to low pressure. Right?
That is also diffusion. Right. Either you basically fine. Okay. Now look at this, people. Right. Say I have a partition, and say here I have a hole. Okay. Say here I have say I have some aqua solution. So I have some solution with me. Okay, I have some solution with me, and say I have say 50% solution here. I'm talking about the mass percentages. Okay, here I have 50% solution. Here say I have a 40% solution. Okay. Now what will happen? Or let me not confuse you. I will just state that here I have 10 liters of water. Here I have 5 liters of water. Right. So eventually what will happen? The water will move through this hole. Is it not? From the higher capacity, right? It is obviously going to move through this hole to the 5 liter side, right? Obviously, it will not happen this side. No. Why? Because this side is only higher, this side is lower, right? This is exactly what is called as diffusion. Okay, fine. We'll first take down the definition for diffusion, and then we'll go for osmosis. Please take down the definition for diffusion. It is the movement of solute particles, or okay, we'll talk in terms of solvent. Okay, fine. So it is the movement of solvent particles. It is the movement of solvent particles from the region of lower concentration, from the region of lower concentration to the region of higher concentration. Okay, so it is the movement of solvent particles from the region of lower concentration to higher concentration, right? Okay, now please understand, people, why is it that the diffusion is happening? From the definition, I think you'll be able to get an idea. Solvent particles are going to move from the lower concentration side to the higher concentration side. Now, if the same definition, if I have to give you in terms of solute, not the solvent, and that time it will be a movement of solute particles from the region of higher concentration to lower concentration. Okay, you can even make a note of it, right? If it is solute, the movement will be from higher concentration to lower concentration. If it is solvent, lower concentration to higher concentration. Please do not muck it up. You don't have to by heart it. It is all purely logical. We'll try to understand this, what exactly is happening here. Okay, fine. So forget about this. Right. Say I have a partition. Okay. Say in this case I have 1m HCl, and in this side I have say 0.5m HCl. Okay, 1m HCl and 0.5m HCl. Right. So assume that through this particular layer I have, will be able to say through this the particles can move. Either solute particles or solvent particles will be able to move through this whatever the separation. Okay, right. Now the very reason why is there going to be a movement, first of all, first we'll try to understand that. Okay, why in the first place the solvent particles or the solute particles, why it has to move, right? The reason is to attain equilibrium. We have already studied equilibrium in our 11th class, right? To attain equilibrium, right? What do you mean by equilibrium? This side and this side, I should have same concentration. That is what you mean by equilibrium. Okay, so if someone asks you in diffusion or osmosis, why is there a movement? You tell them that they move because they want to attain equilibrium. Equilibrium in the sense on both sides, the concentration should become equal. Now they are not equal. 1m and 0.5m is there, right? So through the movement, right, I am going to make sure, or the system is going to make sure that these two concentrations are going to become same. That is why the movement is happening. Okay, fine. Now, how the movement is going to happen? Right. Now, please understand, people, this concentration 1m has to decrease, right? And this concentration has to increase. Only then the concentration will become equal. That is very easily understood, isn't it? This concentration has to decrease, this concentration has to increase, so that these two concentration on both sides become equal. How is that possible? Right. Now you see, obviously higher concentration means this is concentrated side, this is less concentrated side or diluted side. Let me call it like that. Okay, this is higher concentration, this is lower concentration. Okay, right. Now, if I have to increase the concentration of this, right? If I have to increase the concentration of this, what will I do? You tell me. See, there are two things, solute and solvent. With respect to solute and amount of solute and solvent, tell me, how do I increase the concentration here? What is concentration? Concentration is amount of solute. Correct. Right. Fine. So how do you increase the concentration this side? I'm talking with, forget about the movement, all these stuff. Generally, I'm asking, if at all you have to increase the concentration of solution, what will you do?
Add more solute.
Add more solute to it. That is one way, right? Say if I had only 2 grams of solute and it is not considered enough, I add another 2 grams of solute, so it becomes more concentrated. Right. What is the other way?
By heating, sir,
Yes, by heating, correct. What is going to happen if I heat?
and the solvent amount of solvent will decrease and
Exactly.
solute.
That's it. Correct. I understand. Right. So there are two ways by which you will be able to increase the concentration. One is by increasing the amount of solute. Right. I can write increasing concentration can happen. Solute increases or solvent amount decreases. Is it not? Right? The two ways by which you'll be able to increase the concentration is by either increasing the amount of solute or by decreasing the amount of solvent. You will be able to make the solution more and more and more and more concentrated. Right? The same exact thing I'll be able to tell for what is going to happen if I have to decrease the concentration. The amount of solute has to be decreased or more amount of solvent has to be added. That is what we go for dilution. Isn't it? Now I think you'll be able to understand which side what will move. Right. Now, let me look into it. If I talk about the solute, right? If I talk about the solute, now please understand this is lower concentration. So the concentration has to be increased. So what has to happen? So tell me from which side to which side the solute, wait, right? So this is a lower concentration side. I want to increase the concentration of this side, right? So from which side to which side the solute particles should move? You tell me. Hope you understand the question, right? From which side to which side solute particles has to move so that this concentration increases and this concentration decreases. Which side to which side?
1 m to 0.5 m, sir. Left to right.
Yeah, from left to right, basically from higher concentration side to the lower concentration side. Very simple. Is it not? This is higher concentration side. This is lower concentration side. And I have to increase the concentration this side. I have to decrease the concentration this side. Obviously, for increasing the concentration, we have mentioned that we have to increase the amount of solute. Where will the solute come from? It will come from the higher concentration side. Right? So the solute particles will move from higher concentration to lower concentration. That is what is given in your definition. But we didn't speak in terms of solute, but I mentioned if it is going to be solute, it is going to move from higher concentration to the lower concentration. Right? Okay. Now, if I talk in terms of solvent, it is going to be exactly opposite, is it not? Right? So now again, same thing. I have to increase the concentration, decrease the concentration. So if I talk about the solvent, right, can I say from this, I have to decrease the solvent, right? And to this, if I have to decrease the concentration, I have to add more amount of solvent, right? So from where to where the solvent will move? The solvent will move from the lower concentration side to the higher concentration side. Solvent particles will move like this, right? Very simple. Only thing you have to understand is how do you increase or decrease concentration? That is first thing. Right now, if you understand with respect to solute, I have, for example, if I have to increase the concentration, I have to add more solute, remove the amount of solvent. This much you understand. This entire stuff is very, very, very easy. Okay. Is there any questions? Even if it's a very, sorry, I didn't understand anything. Even if it's like that, please tell me. Is everything okay here? Did you understand, first of all, higher concentration, lower concentration? Diffusion is going to happen. Why diffusion is going to happen? To make sure that there is equilibrium between both the sides, right? And how solute particles and how solvent particles will move from which side to which side is everything in your fingertips. Everybody understands. Yes, I hope everything is fine. Is there any question?
No doubt, sir.
Okay, I suppose everything is fine, right? If there's anything, please ask. Please ask. Okay. Fine. So this is diffusion. This is only osmosis also. Okay. Now, what is again osmosis? If I have to tell you the definition for osmosis, please take down. I'm going to give you the definition for osmosis. Right? We saw diffusion. It is going to be exactly same, but there is going to be a minor difference. Okay, I'll tell you what is that. Okay. So osmosis, the definition I'm telling, please take down. It is the movement of solute particles, or you can even speak in terms of solvent, not a big deal, right? I'm speaking in terms of solute. Okay, so it is the movement of solute particles from the region of, it is the movement of solute particles from the region of, tell me, can you complete the statement? It is the movement of solute particles from dash region to dash region.
Higher to lower.
Right, higher to lower, right? It is the movement of solute particles to the region of higher concentration to the region of lower concentration. It is the movement of solute particle from the region of higher concentration to the region of lower concentration through a semi-permeable membrane. That is the definition, right? Movement of this region to this region through a semi-permeable membrane. I think if you are finding it difficult for the spellings, semi-permeable. This is permeable membrane. Okay, so in short form, we call it as SPM. SPM is semi-permeable membrane. Okay, right. So this is what is the, from the definition, I think you'll be able to understand what is the difference between diffusion and osmosis, right? Diffusion, there is no requirement of SPM, right? But for osmosis, we require a separation. This separation should be an SPM. I'll tell you what is an SPM, don't worry, right? But this separation should be an SPM, semi-permeable membrane. Okay, I think you would have studied so many. I think you should have at least known this term, semi-permeable membrane, in biology, in your 10th class biology or something. Your cell wall, right? Your cells has a wall, the membrane, cell membrane. All these are semi-permeable. What do you mean by semi-permeable? They will allow certain substances to go through, and they will not allow certain substances. It's like a watchman, right? So if a known person comes, maybe he'll allow. If an unknown person comes, he'll not allow. Same thing here, right? So SPM is a semi-permeable membrane. Permeable means permission, right? So it will give permission for only certain substances to go through, and other substances cannot go through. It's like that. That is what is called a semi-permeable membrane. Okay, right? So if in the process, if there is an SPM, it's called osmosis. If there is no SPM, it's called diffusion. But the movement of solute or solvent from this region to that region is going to be same. Okay, right? Fine. Now we started all this to study this one. What do you mean by osmotic pressure? Is what we are going to study. For that, we have to understand obviously what is osmosis, what is SPM, and all that. Okay, so we'll try to understand. Okay, but what is the time? Okay, 10 more minutes. Okay, now let me construct an osmotic setup, a osmosis setup. Okay, right. Say, okay, this is, assume that this is higher concentration side, this is lower concentration side, and this is an SPM. Okay, right. Now we'll talk only about the solute. Okay, so you're talking about the solute. I know from which side to which side the solute will move. Obviously, as you said, it is going to be from higher concentration to the lower concentration. Okay, from this side to this side. Okay, now what I want to do is, what I'm going to do is, in the lower concentration side, I am going to apply some pressure. Okay, right? See, the natural movement, forget about if this is not there, if this pressure I'm not applying, what is the natural process? Natural process is osmosis. Movement of solute particles from the region of higher concentration to the region of lower concentration. Like this, the movement will happen. The solute particles. Okay, now what I'm doing is I'm applying some pressure on the lower concentration side, just enough to stop osmosis, just enough so that this movement is not happening. Okay, right? Again, I repeat. Natural phenomenon is the movement of solute particles from this side to this side. That is osmosis, that we understand, right? So what I'm doing here is, in the lower concentration side, I am going to exert some pressure, and the amount of pressure is just enough that this movement of solute particle is not happening. That means osmosis is not happening, right? Now that value of pressure, that value of pressure which is required to just stop osmosis, that pressure is what is my osmotic pressure. Okay, fine. Now I'm going to give you the definition. Please take down this diagram first, right? And then I'll give you the definition for osmotic pressure, right? So again, we'll speak about it, right? The pressure which is just enough to stop osmosis is what is called as osmotic pressure. Okay, fine. You take down this diagram, and then I'll give you the definition for osmotic pressure. Okay, fine. So osmotic pressure definition: it is the amount of pressure. It is the amount of pressure to be supplied, or to be not supplied, applied, to be applied. It is the amount of pressure to be applied in the lower concentration side, in the lower concentration side, to just stop osmosis. To just stop. I don't want to do anything else. I just want to stop the movement, right? To just stop osmosis. That pressure is what is called as osmotic pressure. I think it's pretty logical to understand. If I exert pressure, obviously this pressure will be higher and this movement will be what to say, stopped. I think it's very logical to understand, right? There is not much explanation required. Okay, fine. Now tell me, if okay, we understood the what is osmotic pressure. Little pressure exerted on the right hand, sorry, on the lower side, lower concentration side, to just stop osmosis. The osmosis is not happening. Okay, now what if I exert a pressure which is more than the osmotic pressure? What do you think will happen? If the pressure applied is more than the osmotic pressure, what will happen? Think about it and tell me. If I apply a pressure which is more than a pressure which is just going to stop the osmosis, what will happen?
The diffusion, sir. That's the movement of solvent will happen, sir.
No, not like that.
Let's move from lower to higher then, sir.
Yes, right. So if you exert a pressure which is greater than the osmotic pressure, now osmotic pressure just stops osmosis, no movement, right? But if you little more increase the pressure, what is going to happen? The opposite is going to happen. The movement of solute particles will happen from lower concentration side to higher concentration side. And this phenomena is what is called as reverse osmosis. Have you ever heard this term? If yes, where?
In
Reverse osmosis.
Aquaguard, all those water.
Absolutely. Right. In all your water purifiers, this is exactly the phenomena you use, reverse osmosis. And how do they do it? With the help of osmotic pressure. For every solution, we know what is the osmotic pressure. So you just have to supply a pressure which is little greater than osmotic pressure. You will end up in reverse osmosis. You know what osmosis is? The movement of solute particles from higher concentration to lower concentration. But if it is reverse osmosis, RO we call it, right? It is going to be movement of solute particles from lower concentration to higher concentration. And we'll try to understand how is it that it is going to purify water. Okay, right. Now, maybe I'll draw the diagram again. How is it used in RO? I mean, how is it used in your aquaguard and stuff is what we're trying to understand. Okay, so this is higher. Okay, now, see, we are talking about concentration, right? And we're talking about water purification. Okay, now the solutes which you're talking about, right? Obviously, water is now considered to be a solution, right? So the solutes which you're considering are all the impurities. Please remember this. Solutes are nothing but the impurities. Okay, right? So now when I say higher concentration and lower concentration, in this side I have more impurities, and in this side I have lesser impurities. That's what you need to understand. Okay, this has high impurity, this has low impurity. Okay, fine. Now if I exert a pressure, on the lower concentration side, what will happen? We said the solute particles will move from lower concentration to higher concentration. That means what? Here I have already lesser impurities. So if I obviously if this is not there, what will happen? The impurities will go from this side to this side, and that will again this side also will get polluted more. But what I'm trying to do now, I'm going to exert a pressure on this side, so that obviously not exactly equal to osmotic pressure. If it is exactly equal to osmotic pressure, nothing will happen, right? But little more pressure than the osmotic pressure, what will you see is the impurities will move from this side to this side. So this side will become more pure, right? Because the impurities are moving from this side to this, not from this side to this side. Already this is having lesser impurity, and still more impurities are going to go from this side to this side. And that exactly is what is reverse osmosis, and this is how we use in all our what to say, aquaguard, bottom stuff. Okay, right. Now the SPM, the semi-permeable membrane, which we can use. There are so many. You can check in your books. There I can have sheep's bladder, right? Or I can sometimes have nitrocellulose, something, agar. All these things are there. Just check in your books. What are the examples for SPM? Or you can just Google it, right? What are the examples for SPM? You can see there are so many examples. Okay, that has to be used. That for reverse osmosis, and that is why in your homes also, the only thing which will be changing is this filter. Okay, through this semi-permeable membrane only the impurities move from this side to this side. Okay, so we talked about osmosis, we talked about osmotic pressure, and we also spoke about what do you mean by reverse osmosis. Okay, the only thing which is left is about what is the quantification, the mathematical representation of osmotic pressure, and how are we going to use this to find the unknown molecular mass. Again, for all colligative properties, one thing is common. As I already told you that with this colligative property, we'll be able to find what is the molecular mass of an unknown solute, and this also will be able. Right? Maybe I'll just give you the equation and then we'll wind up. Okay, fine. The equation is very simple, right? I'm going to give you that. Very simple equation. I am just going to use PV is equal to nRT. This we have already studied in your 11th class, ideal gas equation. Okay, but not exactly, but anyways, we can take it. So what I do is P, I keep it this side, and I write N by V RT. What is this N by V? What is N by V? Number of moles per volume is what?
Molarity.
Right? That's it. This is what is the equation you're going to use. So forget about all this. So the equation which you're going to use is pi is equal to C into R into T. Right? This pi is my osmotic pressure. Okay, this C is the molarity of the solution. R is the universal gas constant, right? And T should be in Kelvin. In this case, definitely it should be in Kelvin, not like previous cases, right? In this case, temperature should be in Kelvin, right? And 99.9% of times, you will be using the R value as 0.0821. Okay, right? So this is the equation for osmotic pressure. Pi is the osmotic pressure, C is the molarity concentration, R is the universal gas constant, that is 0.0821, and temperature is T, which should be in Kelvin. Very simple equation. Okay, pi is equal to C into R into T. Okay, I understand. You understand how it comes from here also. N by V is molarity, T is here, R is here, T is here. It comes in the ideal gas equation. But again, you're not worried about how it came, where it came from. You do not know the equation. Okay, any questions, guys? I think we're going to wind up here. Tomorrow, in next class, whenever we see, we will do some problems on this. A lot of problems we'll do on this. And we're going to see the last part of this. I think I will take maybe. I think I should be completing by next class. If not, maybe half an hour of the next class I will take and I will complete this chapter. Okay. Is there any questions, people? Is there any problem? Okay. If not,
No doubts.
well, yeah. If not, we'll wind up. Thank you so much, guys. I'll wind up the class.
Sir,
Thank you.
Yeah. Please tell me.
cane sugar question I asked now, sir. I tried with the calculator,
Okay.
95 value. I got 4.08, sir.
4.08 is correct. No. 4.08 is a depression and freezing point. What you have to find? You have to find the freezing point. So you have to do what? What happened? So 273.15 minus whatever the value which you got. 4 point something you are telling. That should be the answer. So 269 is coming, no?
Yes, sir. But I also got 269 with 3.88. Like I got 3.88 and I divided by 100.
Okay. So that maybe the
Only
that'll
the
be very
decimal value differs. Sir.
correct. So like this only you have to do Kana, because looking at the decimal value they'll cut points.
Okay.
Maybe half a mark they'll cut. Okay, even though your answer is correct, right? But these kind of situations they'll cut marks and unnecessarily you lose marks.
Okay, sir. Thank you, sir.
Okay, right, fine, cool. Thank you so much, people. We'll meet again
Thank
next
you,
Sunday.
sir.
Sir,
Yeah, tell me, Kana.
I joined today only. So
Okay.
how do I catch up?
Speak to the management. You will have recorded videos. We have
Okay.
seen around I think 3 classes, or I think 3 or 4 classes. I'm not sure. I take physical chemistry and inorganic. I think some other faculty takes organic. So solutions chapter we have completed almost 2 to 3 classes. This is the 4th class, I guess. I'm not sure. So you can go through the recorded videos, and also I can. This is not only for you. I think most of you will have my number, but for those of you who don't have my number, 8939219916 is my number, right? If you find anything, any difficulty, you can please ask me. WhatsApp me, I'll be.
Thank you,
Okay.
sir.
Right? Cool. No issues. Fine. Any other questions, people? Any other clarity? Okay.
No, sir.
Fine. Cool. Thank you so much, people. We'll see next week.
Thank you, sir.
Yeah.
Thank you.
Thank you, sir.
You.